In this video, I'm going to explain my project, which is two power inverters. So for this one, it's a square wave power inverter, and the large one is a pure sine wave power inverter. And for both of them, I designed the 4-layer boards. So this one for the square wave power inverter, and the other one is for the pure sine wave power inverter. And next, I'm gonna demonstrate both of them. So for the square wave power inverter, I'm using a 12-volt that's connected to the oscillating circuit and 32-volt connected to the center tap of the transformer. And I'm gonna run it, see the results. And so I'm having 122 volt AC, and this is the sine. This is the wave. So for the pure sine wave, I'm using a 24 volt as the main input, which is connected to the back of the box. And inside I use two buck regulators, 5 volt and 15 volt, to supply the other parts. And now I'm gonna run it. So it's pretty much a sine wave with 60 hertz and 412 RMS. There's light. It's 128 volt AC. For the modified sine wave power inverter, I used the 555 timer to generate a square wave, and I needed two signals, so I used the BC547 to generate the other signal for me. So the output of the timer will control the base of the transistor. So whenever it's high, the transistor will ground this line, so there is no output. And whenever it's low, I will get the low signal in here. And I use this resistor, the 120K, to give me the frequency as 60 hertz. And I have the MOSFETs. I have 16 of them, so I have 8 in each side, and they are connected in push-pull methodology. So the output is the V drain and the ground, which will be connected to the transformer to step it up. And I have the signals that's coming from the oscillating circuit, which is the 555 timer and the BC547. I have the high and low, so each signal is connected to one set of the MOSFETs. For the pure sine wave, I have used multiple pages for the schematic. So the first page is the microcontroller, and I have used the 5-volt signal to supply the chip, and they have these pins are connected to the header, and it will be used to connect the debugger to it so I can control it and program it. And then I have the gate drivers, so I have 6 of them. Each two will supply a complete etch bridge. So I have the signal that's coming out of the controller, B1A and B1B, and these two signals will be feed to the gate drivers. So the gate drivers will receive the signals, and it will drive it to the MOSFETs through these signals. So I will have from each gate driver 2 signals. Here I have the sets of MOSFETs, so I have 12 of them. Each 4 will be one etch bridge. So in here I have the high signal that's coming in from the gate drivers and the low signal, and then the second gate driver will feed the other set of them. So I have 24 volt DC connected directly to the MOSFETs, and they have the output signals, which are the VO negative and VO positive for each etch bridge, and they are connected in parallel. and then I have the 5-volt regulator, which is LM2567, and then I have two 15-volt regulators, and they're used to feed the gate drivers and the 5-volt to the microcontroller. For the layout, I have designed a 4-layer board, so I use the top and bottom layers for the traces, and then I have two plane layers are connected to the output of the MOSFETs. So each layer will handle one um, side of the output of the MOSFETs. And they have placed the MOSFETs in this way so I can connect the heatsink to them. So I have layers in here. So I have the top and the bottom, which are for the traces, and then I have the two plane layers. And here's the 3D view of the design. For the layout, I have designed a 4-layer board. So I have the top and bottom layers, I use them for the traces, and I have the V drain and the ground, which are the output of the MOSFETs. I have placed the MOSFETs in this shape so I can connect the heatsink to them. And for the other components, I place them by room, so it's become easier for me um, to know how to connect them while I'm doing the soldering. And here's the 3D view of the design.